So what we have here, what we learned from J.J. Thomson, Robert Millikan, Ernest Rutherford, and Marie Curie, okay? All of their results, okay, all of their results combined helped us. That, for one, atoms are mostly empty space. This diffuse electron cloud is mostly empty space. There is an extremely dense and massive core in the middle, okay? And that makes up the vast majority of the mass of the atom. So for example here, if we look at the masses of the electrons now, so here in unit of kilograms, okay, 9 times 10 to the minus 31. It's crazy small. Protons and neutrons to the minus 27. That's still extremely small. But consider the difference between these, right? This is a factor of 10,000 times. So the protons and the neutrons are 10,000 times more massive than the electron. And so the vast majority of the mass of an atom is in the nucleus, in the protons and the neutrons, okay? And then the charge, they were able to discover, right, the electron is -1, the proton is +1. So when we write charge in chemistry, just to not confuse negative numbers, you'll see us write the sign on the right side instead of the left. You're probably used to seeing this. You know, that means, let's just be clear, -1 as like the number. Okay, this is -1 charge. Okay, we write it that way just so we know we're not talking about negative numbers, we're talking about the charge. But now look at this little asterisk right here. The magnitude and charge of the electron and proton is. So that means the electron is -1.60 times 10 to the minus 19 coulomb. That's a very, very small number, okay? And then the proton is positive 1.60 times 10 to the minus 19 coulomb. And what we do, and so now I put the negative sign because that negative sign is in reference to that C for coulomb, okay? So now what we do in chemistry, we say this is all equivalent to 1 minus. And we say this is all equivalent to 1 plus. So in this class, when you see us write 1 minus and 1 plus, or even 2 plus, 3 plus, 4 minus, it's really this number, you know, times 2 or 3 or 4, whatever the number is, okay? You don't have to memorize numbers. I'll always give you numbers. But recognize that the charge of a single electron, single solitary electron, is a tiny, tiny number. Okay? Of course, if we have a lot of electrons, like billions and trillions of electrons, then we would have quite a lot of charge. Okay? So we're going to build that up here as we go. Okay. So now, here's a cool analogy for you for the structure of the atom, okay? So the size of an atom is roughly 10 to the minus 8 centimeters. That's tiny. That's 1 over 10 billion centimeters, right? It's really, really tiny. And that's the size of like the whole atom itself, right? Where keep in mind, this is mostly nothing, right? Some diffuse electron cloud. However, in the center, there's that really dense and massive nucleus. And it's about 10 to the minus 13 centimeters. So that's 1 over, let's see here. That's going to be 1 over 10 trillion. Excuse me, that's not 10 trillion. You get the idea. I can't think right now off the top of my head. It's crazy small. It's crazy, crazy small. So the difference between 5 and 8, that's a factor of 100,000 times smaller. So the nucleus is 100,000 times smaller than the atom itself. So here's an equivalent analogy, okay? Here is where we would be sitting if classes were, you know, back to normal, face-to-face. There's HSU's campus in Arcata, all right? And all the way up about 35 miles away is the entrance to Redwood National Park. Beautiful. When you get up here, if you're not up here yet, it's absolutely stunning. You got to make this drive up the coast. Beautiful drive. get all the way up here. You pass the lagoons, you get into the entrance to the park. It's just gorgeous, okay? So that's a 35-mile drive. Now imagine if I took a basketball that's roughly 30 inches and I placed that basketball in the middle of the highway on this stretch of road, 35 miles, okay? Now imagine I made a radius, or excuse me, I made a diameter out of that road, right? 35 miles as my diameter. So some crazy large circumference that goes way out into the ocean and so on. This would be our relative scale of the atom. If the basketball were the nucleus, okay, then that means that the size of the atom would span from HSU all the way up to the Redwoods, and all of this stuff in between would be nothing. It would be vacuum. All of that ocean, all of the mountains, all of these redwoods, all of you people, if you're in this circle, it would be nothing if the nucleus were the size of a basketball. Pretty amazing. Another equivalent analogy is if you took a marble, I don't have one right here, but imagine like a regular old marble, glass marble, and we put it in the middle of a football stadium. The entire football stadium, like, you know, something like professional sized football stadium, like not Redwood Park, or the Redwood Bowl, but like some huge big ass stadium, okay? So that would be the size of the atom if the nucleus were the size of a marble that we put in the center. And of course that football stadium, it'd be all vacuum, right? Nothing is in it. Amazing, just how much empty space there is in an atom. And if you think about it, the entire universe is made up of atoms, right? This table, me, the air I'm breathing. And atoms are mostly empty space. So what does that tell us about the universe? It's kind of sad, but I think it's kind of beautiful. The universe is mostly empty. That is true. That is factual. Even this solid table is mostly empty space. It's amazing, right? Completely amazing. Okay. Oh, yes. Black Lives Matter. Okay. So finally, let me back up. So sorry. I forgot the slide was coming up. I forgot what order it was in. Okay. So just to summarize. Okay. What we learned from J.J. Thomson, Robert Millikan, and Ernest Rutherford and Marie Curie. Okay. We learned the structure of the atom. Here we go. Right here. Understand the Rutherford model and the structure of the atom and its basic components. So that kind of story, that long-winded story I gave you, is all about the Rutherford model of the atom. Okay. So now what I wanted to say here, so all these folks that we talked about, they're legends, right? We memorialize them. We know their names. We name atoms after them. We name units after them. I wanted to tell you about some folks that maybe you've never heard about, okay? Black Lives Matter, Black Chemists Matter, okay? So this is a really cool document made by the American Chemical Society, right there. 5 black chemists who made a difference. So I would highly encourage you to read about these folks. These folks have made some amazing contributions to science. And obviously there's a lot more than 5. This is a really cool infographic that was made this year. Black Chemist Week was August, oh, I can't write. It was August 12th through 19th this year. So that's when this document came out. Okay, so just the week before we got to school was Black Chemists Week. So I put a bunch of stuff on my Twitter. You should check that out. So just to highlight a few of these folks, Mae Jemison, first African-American woman to fly in space. And she has a BS in chemical engineering. That's amazing. It's already difficult enough to get a degree in chemical engineering. And then she went and became an astronaut. Yeah, girl, do it. And that happened in 1992. And she was also the first astronaut to appear on Star Trek. Pretty cool stuff. And then one more person I'll point out from this list, George Washington Carver. He was born a slave and died a PhD scientist. Incredible, amazing, okay? So read about these people. You can go to this website here, Check it out, y'all.